Okay, hi everybody. So here we have our familiar function. We're trying to minimize it this time, restricted to the unit circle. So we have to explain what Lagrange multipliers does to solve this constrained optimization problem, with the constraint being the unit circle equation. Okay, so first I'm going to draw pictures because there's no way I would remember this without having some good pictures. And actually, I'm going to draw two pictures of two different points. So like one point Q and then another point P. And they're going to be in both my pictures. And so here I'm going to show that Q is not a critical point and see what that looks like. And then here I'm going to show P is a critical point, and we'll see what that looks like. Okay, so in both cases, so to look at Q, we're going to look at the tangent space at Q. And when we look at P, we'll look at the tangent space at P. Okay? And actually, the circle equation, so I'm going to actually introduce a formula. The circle is the constraint, and we're going to view it as a map, taking xy to the number x squared plus y squared minus 1. And so then the circle here, this blue circle, is the preimage of 0. And actually, we're just going to take the gradient of the constraint equation. So restricted to the unit circle is the constraint. So I chose to call this map C for constraint. And what's the gradient? Well, in this case, it's pretty easy. Partial with respect to the first variable goes there, comma, then take the partial derivative with respect to the second variable. And that goes there. Okay, that was an easy gradient to take. Now, why do we care about this? Well, because at any point, the gradient of C at that point will be 90 degrees. And so it gives the normal space, which is at 90 degrees with respect to the tangent space. At a different point, we'll get a different gradient vector pointing in a different direction, the gradient of C at this point, P. And so now we realize that, originally we were taking the gradient of our function g, and that was going to tell us things. So actually, that gradient works too. So maybe at the point Q, the gradient of g at the point Q will look like this purple vector, and that is why it's not a critical point. It's not critical because we can project it, and we get a non-zero projection. So this is the W equals projected gradient. Which one? We have two gradients. Well, we're projecting grad G to the tangent space. Okay, and you can see that W is not the zero vector. Okay, and that's why it's not a critical point. Now, we can imagine, what does a critical point look like? Well, if this projection vector is the zero vector, then actually the gradient had to be along there. So in this picture, I'll draw the gradient, and it actually looks like this. Something like that. So at this different point, P, which is a critical point, the gradient is in the same direction as the gradient of the constraint. So the gradient of our objective function, I called it f here, should be, right, our objective function, we want to minimize the function g, and that gives us a gradient. But then we also have the constraint equation. The unit circle is given by this equation. And so that, maybe I'll put that in orange because that's what so that one is here. And so these are the two pictures. This is a picture of a non-critical point. The projected gradient is non-zero. And so this gradient and that gradient point in different directions. But P is a critical point, and that means both of these gradients point in the same direction. And this is what Lagrange multipliers takes advantage of. So now I will explain part A, Lagrange multipliers, in this context of minimizing G restricted to the unit circle. Okay, so part A, how do I explain it? So Lagrange multipliers views the constraint equation as a map and takes its gradient. And so, I guess I put the formulas up here, but I can at least give the name, map C, and takes its gradient, grad C, right? And then what does it notice? So Lagrange multipliers notices this. It notices that these gradients have to point in the same direction whenever P is critical, and use the gradient, and notices that at critical points P in the input space, satisfying C of P equals 0, and I should put that in a formula color. Oh, not resize, color formula. The two gradients point in the same direction. Okay? So this is the key idea of Lagrange multipliers. And now it converts this into an equation. This becomes a vector equation. And let's now put that in a formula. That P is critical. So we're looking for a P in xy equals x comma y, such that the gradient of our function we're trying to minimize at the point P is equal to some scalar multiple of the gradient of the constraint at P. And here I'll just put that, what's this? So some scalar multiple. And this is a Greek letter called lambda, usually called lambda. I think for like L for Lagrange multipliers, but it's just some real number. It's some multiple of this vector. Okay, so this equation right here, this equation matches this picture. Okay, so this equation and this picture are saying the same thing, okay? And so now let's step back and say, well, we need that to be true and that C of P equals 0. That's this equation here, but I'll just repeat it. And that translates into the x squared plus y squared minus 1 equals 0, where C, I turned that equation, the equation of a circle, into a map. And so the point, in order to actually be on the unit circle, we need that this point P satisfies the map. And C of P equals 0, so that P is on, or maybe I say satisfies the constraints, so that P satisfies the constraints. So this equation makes sure that P satisfies the constraints, and this equation makes sure that the projected gradient will be 0. So you see that whenever they're in the same direction, if we project, we get the 0 vector. Whereas here, if they're in different directions, we project and we get a non-zero vector. It's not a critical point. Okay. So I think that's part A. Maybe one more thing I will say. So Lagrange multipliers finds critical points as the solutions to a system of equations, this system right here, a system of equations in more variables. And the point here is we introduce a new variable, and I'll even call it that, new variable lambda. Whereas over here we have old variables x and y. Okay, and so in this case it'll be 3 variables. And so then part B just says explicitly write down those equations. Explicitly write them down. Okay, so we can do that. So first of all, we definitely need that this equation becomes, so here I'll put part B. Part B, explicitly write down the equation. So x squared plus y squared minus 1 equals 0. That's the first equation. We need 2 more equations, actually, because this single vector equation becomes 2 normal equations. Oh, and let's actually see what that is. So we know that here, I'll even put it over here. What's the gradient of g? Let's compute that real quick. So the gradient of g maps R2 to R2, and it sends xy to the vector 8 x to the third. And I just have to keep taking the derivative. Okay, now I'll take the derivative with respect to y. Okay, and so yeah, so let's just take this. It's gonna, and what do I see is that I get, okay, well, let's just rewrite this equation up here. Grad g of p has to be equal to f of p. And so this needs to be equal to lambda times 2x 2y. And what we see is that if we look at just the first component, we get one equation, namely, okay, now I'll write it over here. I'm going to pull it down later. 8x to the third plus 2y squared minus 2x equals lambda times 2x. That's the equation that comes from the first component. And now let's look at the second component. So lambda has to obviously come in here. It's a scalar, it's a real number multiplying this vector. And that will give us lambda times 2y. Okay, and these are our last 2 equations. So let me just pull them down here. And this, these 2 things up here become these 3 equations. 3 equations in 3 unknown variables, x, y, and lambda. So that's it. Did I do everything? Wow, I think so. Explained Lagrange multipliers that really needed these pictures that have labels, and then this explanation of what's going on in words and formulas. Then part B said, so these are formulas. These are definitely formulas, but we can make them very, very specific for our problem, actually compute the gradients, and see what these equations are in full detail. Okay, good. So that was me quizzing myself. I quizzed myself on this problem, and here is my previous solution to this problem. So you can take a look at that as well. This actually was a little bit nicer, I think.